Alright, ladies and gentlemen, here is the big practice test that I gave you on Friday. If you notice, there's an extra page there, which makes it even super duper long. Keep in mind, I gave you a lot of practice questions. Doesn't mean the test is actually going to be this long. Expect between 20 to 25 questions. If it ever goes above 25, maybe one extra question. I have to double check my actual test paper. Oopsies. But anyway, it's definitely more than 20 questions, definitely less than 30. Should be around 25-ish. Please expect that. Don't panic. But anyway, we start with number 1. Which graph best represents the greatest amount of work? Alright, let's look at these keywords, work and graph. We should be thinking area under the curve. Okay? So we're looking for the graph with the most shaded area beneath the graph. And that, ladies and gentlemen, should be easily discernible. That's choice B. If you want to calculate numerically in the event they ask you to calculate for it, then we need to look at the area. So here, base times height, that's for a rectangle, but if it's a triangle, it's 1/2 base times height. So choices A and C are dealing with triangles, so 0.5. Okay, so this one has a 2. This one is the same as A. This one's 4. And this one is 2. Okay, so there's only choice B with the greatest amount of work done. Number 2. Through what vertical distance is a 50 Newton object moved if 250 joules of work is done against a gravitational field? So they gave us the weight of the object in newtons. They told us we exerted 250 joules, and we're looking for distance. Remember that work is equal to force times distance. The force is always in newtons. So that should be 5 meters for D. Okay, number 3. How much work is done on a downhill skier by an average braking force of this many newtons to stop it in a distance of that? (9.8 times 100 is 980 times 10, 9,800, that's choice D. Number 4, a 20 Newton force is used to push a 2 kilogram object a distance of 5 meters. And that's simple, straightforward calculation. Number 5 says the rate at which work is done. So if it were just asking work, choice B would be correct, joules. However, they say rate of work. That is always power. And power is measured in watts. Okay, rate or time rate of work, that's power. Now we're going into those types of questions. Power is equal to work over time, or you could expand it to look like this. So let's look at number 6. If you decrease the amount of time, if time decreases, what happens to the power? Notice that time is in the denominator. So if you divide by a smaller number, you're going to get a bigger number. Versus if you increase time, you're dividing by a bigger number, so you get less power. So here we're decreasing time, making it smaller. We're doing things faster, so we have more power. So time goes down, power goes up. Number 7. A small electric motor is used to lift a 0.5 kilogram mass at constant speed. If the mass is lifted a vertical distance of this in 5 seconds. Okay, mass is 0.5, distance is 1.5, time is 5 seconds. We're looking for power, so we're going to use this one. Keep in mind, if they give you mass and you're lifting it vertically, we need to change it into a force. That means finding its weight, multiplying by 9.81 divide all this by 5, and you'll get that power is equal to 1.5 watts. So 0.5 times 9.81 times 1.5, divide all that by 5, and you should get 1.5 watts. All right, number 8. What is the maximum amount of work that a 6,000 watt motor can do in 10 seconds? All right. $6,000 times 10 will get us the work. That'll be 60,000. That's choice D. Okay, this time we're going to use the last variation of the power equation because they gave us the power. And the force right here. 58,000 divided by 21,000. That'll give us almost 3.6 meters per second. My mistake, I did that math wrong in my head. That's 2.8 meters per second. Oopsies. Now we move on to number 10. What is the maximum height to which a motor having a power rating of 20.4 watts can lift a 5 kilogram stone vertically in 10 seconds? Alright, again we're using power is equal to Fd over T. Making sure you turn that mass into a force. So you have 20.4 equals 5 times 9.81 times D over 10 seconds. Okay, if you solve for D, you should get about 4.16 meters. Yeah, that should be it. Yeah, that makes sense. Okay, because I just did that in my head. Alright, number 11. What is the power output? Another power question. When does it ever end? Okay, what is the power output of an electric motor that lifts a 2 kilogram block 15 meters in 6 seconds? So keep in mind, commonly they give you the mass in kilograms, so you typically have to multiply by 9.81. In the event they give you the weight in newtons, then you don't have to multiply by 9.81. It's only if you have a mass and you need to lift it vertically that you have to change it into newtons by multiplying by 9.81. That's 15 divided by 6 seconds. Alright, do the math, plug and chug. And you should get approximately 49 watts as your answer. Keep in mind watts and joules are different. Joules is the unit for work. Watts is the unit for power. Alright, now we finish with the power section. Let's move on to kinetic energy. Alright. If the direction changes and its speed remains constant, which quantity must also remain the same? Velocity might seem like a good go-to answer. However, velocity is dependent upon direction. So if direction changes, velocity also changes, so that's not it. Same thing with momentum. Displacement is also the same. Now, if you notice, all three of these answers are vectors. Kinetic energy is the only scalar that doesn't depend upon direction. Remember, vectors account for direction, so if direction is changing, these vectors are also changing as well. Scalars don't depend on direction, so they stay the same if their magnitudes stay the same. And that's it. Okay, number 13. Compared to the kinetic energy of block A, the kinetic energy of block B is what? Alright, so that means we gotta use dummy variables. So I'm going to do A right here, pretending its mass is 2, given in the problem, and its speed is 1. Now for object B, it's half the mass, so it's just going to be 1, but it's double the speed, so that's going to be 2. And that'll come out to 2. So notice how much more of an effect the velocity has because it's squared. So block B has twice the amount of energy if you just play around with dummy variables like that. Alright, number 14. As an object moves upward at constant speed, kinetic energy will also remain the same because constant speed. Now, number 15, as a bullet shot vertically upward rises, the kinetic energy decreases. Because if you think of an object being thrown upward because of gravity pulling down, it slows down as it goes up. So think of objects being thrown upward, it slows down, so kinetic energy decreases. Okay. Now, how is it different from 14? So the key word there is constant speed, so kinetic energy stays the same. 15, on the other hand, has no such other outside thing to keep it going constantly, so that's why it's just decreases, because typically it decreases, but 14 has that additional keyword of constant speed, tells you that kinetic energy remains the same. 15 doesn't. Alright, a 75 kilogram bicyclist coasts down a hill at 12 meters per second. What is kinetic energy? This is straightforward, plug and chug. Okay. I don't know how many of you have been watching the Olympics lately, but I've been on top of that, especially if you know me, I am a huge figure skating junkie. Alright, plug and chug. Let's pause this for a moment and calculate. You should get 5,400, which is choice C. Okay. Number 17. If the speed of a moving object is doubled, the kinetic energy is quadrupled. Remember dummy variables? So let's pretend originally that everything is equal to 1. That's what you get. Now if you double the speed, then it becomes that. Now we just got to pay attention to the difference here. 1/2 to 2, that's quadrupled. Okay. Number 18, the gravitational potential energy with respect to the Earth that is possessed by an object is dependent on the object's what? So potential energy is based on position or condition. So it's not based on acceleration, it's not based on momentum, and it's not based on speed. It's based on position. Let's look at this equation. H is the deciding factor here. It's based on position, it's based on height. None of these other variables can come into play here. Alright, number 19, which describes a system with decreasing gravitational potential energy. So we're thinking about something that's going down in height. So it's not A, it's not B, it's not C, it's D, because he's going down, decreasing height. So what is the potential energy of a diver located 3 meters above the water? Plug and chug. You know, my favorite figure skaters are from Russia, from Japan. If you've been watching the team event, Canada's winning. The maple eaters. No, I'm kidding, I respect Canadians. I love maple. Okay. 75 times 9.81 times 3. Let's do this math. You should get 2,207 joules. Okay, so that's choice B. Number 21. An object weighing 15 newtons is lifted from the ground to a height of 0.22 meters. The increase in the object gravitational potential energy is approximately, same thing, plug and chug. Alright, now key thing here, they gave you the weight in 50 as newtons. So that already is mg. If they give you the mass in kilograms, then you multiply by 9.81. If it's in newtons, you don't have to do that. Okay, and that should equal this, choice C. Number 22. Now we're looking into spring potential energy. Let's use purple because I like purple. It's the color of royalty and regalness. Okay, we're looking for this. 1/2 kx squared. They gave the spring constant k. And x, we don't know. So we got to do this extra step. So that means they gave us, surprisingly, the force in a spring. So we got to resort to this equation. So there's going to be probably a question where you have to utilize both of these spring equations to solve what you're looking for. Okay, so this should equal 0.3 meters, which we plug in all the way over here. Don't forget to square it, so 0.3 squared times 4 times 0.5. And that should equal, oops, I did this wrong, 0.3 squared times 4 times 0.5. And you should get 0.18 joules, and that's choice A. Whew, that was a lot of questions. All right, number 23, conservation energy time. So here we have an object, a cart moving with kinetic energy, and it bumps into a spring. So all of that kinetic energy now becomes spring potential energy compressing the spring. Okay, so kinetic energy becomes spring potential energy, which is now equal to 16 joules as well. All right. We're looking for K, the spring constant, and it tells us it compresses 1 meter. So 16 equals 1/2 K times 1 squared. Okay, let's do this math. 16 divided by 0.5, and that's 32 newtons per meter. Choice A. Number 24. Spring with a spring constant of 80 newtons per meter is displaced 0.3 from an equilibrium position. There's potential energy in the spring. Okay. That's K. 0.3 is our X. That's squared. 0.09 times 80. So we get 3.6 joules is our answer. Now, as the spring is stretched, so that means it's increasing X. What happens to the potential energy? That should also go up. The more you stretch it, the more you compress it, the more energy it has built up. Simple as that. Numbers 26. How much work must be done to stretch the spring 0.4 meters? Now, again, force is on the Y, distance or X is on the X-axis. So this is almost like a work on a graph question. So when they say work done on a spring, and if they show you a graph, again, that's area under the curve. So it's a triangle, 1/2 base times height. So our base here is 0.4. Our height is 24. 0.4, 0.2. You should get 4.8 joules as your answer. That's choice A. Now, on the other hand, if they give you a graph but they ask you for a spring constant, that should ask for the slope of this graph. Okay? So we pick 2 points. Let's pick the 2 endpoints here. So remember that slope is equal to delta y over delta x. So delta y goes from 1 to 0, and the x goes from 0.4 to 0. 1 divided by 0.4, you get 2.5 newtons per meter. That's choice B. Now we have a spring force question. Okay, that's our answer, 6.25 newtons, which approximates to 6.3 newtons as our answer. Alright, number 29. Here we have a pendulum swinging from position A to position B to position C. So what happens as we go from A to B to C? So keep in mind, let's label our positions. A and C are the highest points, so that's max potential energy here. Whereas position B is max kinetic energy. So potential energy changes to kinetic energy and then changes back to potential energy as it swings back up. So let's look at each of these statements. Potential energy at A equals kinetic energy at C, that's incorrect. Speed at A equals speed at B, incorrect. Potential energy at B equals potential energy at C, that's incorrect. And potential energy at A equals kinetic energy at B, that's correct. So all that max potential energy converts completely to max kinetic energy down here, and that's correct. Alright, as a pendulum moves from the bottom of its swing to the top of its swing, so B to C, we should expect it to slow down. So A is incorrect, B is incorrect. Now, how about potential energy that's based on height? Going from bottom to top, it should increase. So that's why choice D is correct. Number 31. What is the approximate speed of the block at point B? So keep in mind, max kinetic energy here, and this is max potential energy that we start with. So potential energy at A initially equals kinetic energy at the bottom at B. That's the final position. mgh equals 1/2 mv squared. Okay, so you plug and chug and do the math, and you should get approximately 10 meters per second as your answer. If you get something close to 100, keep in mind, don't forget to take the square root because velocity here is squared. So take the square root to find v. Now let's change the color because I like other colors. Number 32. As the block moves from point A to point B, the total amount of gravitational potential energy changed to kinetic energy is approximately what? Alright, so this is a follow-up question. So as the block moves from point A to point B, what is the total amount of energy changed? So we could find MPE equals MGH to solve this. Because all that potential energy at A equals kinetic energy at B. Okay, and that's approximately 500 joules. Okay. Number 33. A 20 kilogram object strikes the ground with that much kinetic energy after falling freely from rest. How far above the ground was the object when it was released? Okay, so this is initial position at the top. We don't know the height. but we ended at this final position at the bottom. And our energy was 1,960 joules, which should also be at the top as well. So we're looking for height. We can only figure that out with the potential energy equation. So this 1,960 equals 20 kilograms because they gave that to us. And then we can figure out the height. So remember, energy at the bottom equals the energy throughout all points, the total energy. So at the bottom we have max kinetic energy, which was converted from max potential energy at the top. Alright. And this should come out to approximately 10 meters, choice A. Okie dokie, number 34. A car uses its brakes to stop on a level road. During this process, there must be a conversion of kinetic energy into what? Now, let's keep in mind, when it's stopping on a level road, we're not changing anything, we're still maintaining the same height. So gravitational potential energy is not the answer, because we're still staying on the same level elevation. Now, should it change into light energy? Do we see any spurts of light shining in our eyes? No. Nuclear energy? Also a no. The only valid answer here is internal energy. Now, if we think about it, once a car steps on the brakes, the driver steps on the brakes and the car comes to a stop, we hear screeching noises. That's sound. And also, rubber tire marks appear on the road. So there's friction, there's heat involved. So that all accounts for internal energy, sound and heat. So we see that conversion of energy existing there. Now, number 35, a child starting from rest at the top of a playground slide reaches a speed of 7 meters per second at the bottom of the slide. What is the vertical height of the slide? Woo! Okay. So we don't know this height. So that's what we should see. Pei equals kef. So we don't know the mass of the child, but if you look here in these equations, you don't need mass because mass cancels itself out. Just in that scenario. And you should see that h is equal to 2.5 meters, choice C. Excellent. So if you notice, I took this page straight out of last year's Physics Regents just because it's a very relevant free response section that I think will be important for you guys to cover. And a similar example you should see on the test as well. So here we have someone going up an incline. Alright. And so when that person's going up, exerting a force over a distance, work is going to be done. So that's why number 1 of this set of questions is asking us for a total amount of work done. Notice here it's a 1-point question, so you don't have to show work. But how we arrive at the answer, you should still know how anyway. So it exerts a force of that many newtons to move 230 meters up this side of the hill. So it follows the actual distance covered. That's work. So 158 times 230 equals 36,340 joules. So that's the answer for the first part. The second part now is 2-point question, so that means you need to show all work. And I'll show you what counts as a 2-point credit answer. So we need to calculate gravitational potential energy gained while moving up the hill. So you start with the equation. You have to do that. Otherwise, I can't give you credit. Now, the next part is substitution with units. So the mass of the skier is 72 kilograms times 9.81 meters per second squared times the height right here of 40 meters. So if you show all this with units, that's 1 point for the work. The second point comes from having the correct answer with units. So you should get 28,252.8 joules. That's your answer. Showing all this in blue will give you 2 points. Now, if you notice, work is 36,000 joules. The potential energy is 28,000 joules. So 28,000 of all that work is converted to potential energy. That means you have some leftover energy for something else. All right, number 69. Right here. Describe what happens to the internal energy of the ski or hill system is pulled up the hill. So work, our total energy, since we don't have friction at all, keep in mind, oh, let me change this into a different color, equals kinetic energy plus potential energy plus Q. Okay, now, kinetic energy, should we think about kinetic energy? So here, this person's moving up the hill, we don't know, at a constant speed. So kinetic energy is not a factor here. So all that total energy is being considered as both potential and internal energy. So as the person's going up the hill, you're doing work. You're gaining potential energy, and also you're gaining internal energy. So here it increases because you're going up the hill. Okay, so the more work you do, the more potential energy and internal energy you gain altogether. Now, what happens to the total mechanical energy as the person is pulled up the hill? So total mechanical is a combination of kinetic and potential. Now, because kinetic is not a factor here, we're moving at constant speed. All of that mechanical energy now is just potential energy. And as we go up the hill, pulled up the hill, we're gaining potential energy, so we're also gaining mechanical energy. All right. If they ask about kinetic energy, what happens to the kinetic energy? In this case, it remains the same because it's constant. So look out for those keywords. Now, if you notice, these bracket words, neglect, friction, is not included here. So that's an indication that we should account for internal energy, hence why it's asked here. If you see this phrase here in anywhere in this problem set, that means we could neglect Q. We don't have to worry about that at all. But the fact that it's not here, we should account for it. And this is how you go through a set of problems just like this. All right. Now that's the entire practice test. Go through each set of different practice problems, Definitely expect the test to be no more than 25 questions, if anything. Maybe 1 or 2 extra, if anything. Definitely less than 30. Do not worry, this is not over 30 questions. Take care, guys. Make sure you go through things enough times, and good luck.